stepping into the breach, his contribution to the business of council and the business of the society over the past year or so. Indeed. Thank you, Mike. I'm going to just say a few remarks and then ask Bob Gatliff to introduce tonight's speaker. Although not directly part of the theme that we've been developing over this session of the new contributions to the 5th edition of the Geology of Scotland, it's beyond the shadow of a doubt that this work in Port Askaig and the Garvelachs is very directly part of these new and exciting discoveries that are part of where the 5th edition, the new 5th edition, is going. And so I'm very much looking forward to tonight's talk, but I'll ask Bob to do the formal introductions, please.
Thank you, Graham. Tonight's speaker, Bruce Levell, spoke to us a few years ago, so some of you might have heard some of this before. Bruce is the geologist that I've known longer than anyone else. When I was still at school and went for interview to be an undergraduate, who should sit next to me but Bruce? And the next time I saw him was in the first lecture that I ever went to. And we've been friends ever since. And our careers went different ways. Bruce stayed on at Oxford and did a PhD and then joined Shell, where he rose to the dizzy heights of chief geologist. And I know some of the people in here spent their life working for him. And now that he's retired, he's joined Tony Spencer, our latest Clough Medal winner, working on the Dalradian rocks in northwest Scotland. And it's a great honor to have Bruce come back again and give what will be even more an exciting lecture than he did last time, which was really stunning. So over to, and don't go on too long, Bruce, otherwise we'll miss dinner.
Thank you, Bob. And thank you, Bruce. You're very welcome. And I'm looking forward, as I say, to what we're going to hear.
Thank you, Graham. Is this one on now? Oh, no. That's on, yeah. Okay. Yeah, thanks. Can the lights down a wee bit more?
Always goes wrong whenever I see.
Yeah. That's perfect.
Okay.
Yeah, that's good. Oh, well, that's fine. That's fine. Yeah. Don't go to sleep. So, yeah, change of pace. We're going to go to the blustery Firth of Lorne. Beautiful blue seas here. You've probably been looking at that. That's a view from the main island on the Garvelachs looking towards the southwest down the chain. What I'd like to do in this talk is talk a little bit about the work that's being done by this group that's been led by Tony Spencer. Tony kind of passed the baton on to me. We're writing a memoir for the Geological Society. Chapter 16 in that memoir is the significance of the work that's been done on the Garvelach Islands by a whole group of people led by Tony. Very ably, very enthusiastically, and very diligently. And this work is basically a detailed description of the rocks by a multidisciplinary group. And what I'd like to pick up on today is what have we learned which is significant for the Dalradian, for Snowball Earth, for glacial sedimentology, perhaps. So take beyond a description, what's the significance of what we found? So, doing something wrong.
You have to recognize the can now, so that should work.
Yeah, there we go. So here's two location maps. We're at the red dot on Snowball Earth. So about 35 degrees paleolatitude next to the Laurentian continent. We'll discuss how hard that snowball was, what kind of snowball it was. And then at a very zoomed in scale, you can see the 5-kilometer scale bar. I'm going to be talking mostly about the rocks which are exposed on the island chain of the Garvelachs itself. I've worked personally less on Isla than the rest of the team. I hope to make good that deficit this summer. What you can see here is the bathymetry, the source bathymetry acquired in the Firth of Lorne. And you can see the relationship of the glacial sequence on the Black Islands to the subcrop offshore. And we're sitting here between the Appin group up towards Mull, towards the top left-hand side, the northwest. And then we've got a southeast dipping section on the islands, which comes up to the Bonnehaven dolomite, and then eventually into the Jura quartzite with some structural complication as you go towards the west. On the islands themselves, there are somewhere between 30 and about 35 numbered diamictites. And these diamictites then can be continued with the Isla succession to complete the section, which is in total about 1.2 kilometers thick. This is the succession. It's divided from the old days into a series of members. Member 1, 2, and 3 are on the islands, and members 4 and 5 are exposed on Isla. Member 1 is characterized by a diversity of rock types. There are the numbered diamictites, of which there are 18 in membered 1. Thank you. There are dolomites, which are shown here in orange, which are intercalated with the diamictites. And then there are in member 1 also the major breccia unit D13, which you can see with the big black blobs. That's a large glaciotectonite. That unit is succeeded by member 2, which is a different character. It doesn't have the dolomites, it has fewer glaciotectonic, less glaciotectonic evidence. It's got a series of diamictites which are intercalated with sandstones, which are largely deltaic, and I think they're lacustrine deltas. I'll show those to you. Member 3 is characterized by intercalations of yet more diamictites with very characteristic white, mature quartzitic sandstone, subarcoses, with large-scale crossbedding. And member 4 on Isla, which is exposed in the road cut outside Port Askaig, if you've been there, and beautifully in the stone which props open the door on the pub, if you've been there, is a large, thick-bedded sequence of diamictites, which are relatively stone poor, very thick, and they look like rain-out tills, marine deposits, also intercalated in the upper part with cross-bedded sandstones. And then member 5 has fewer of the thick-bedded diamictites. It has some siltstones and some minor carbonate material as well. So each member has a distinctive character, and in total there are 47 numbered diamictites through the sequence. The base of the sequence passes downwards into the Garvelac limestone and is conformable, and the upper part of the sequence passes up into the Bonnehaven dolomite, is conformable. And in that sense, it's a very unusual Sturtian succession because you don't have clear unconformities at the base or at the top. So you've got the complete section in a subsiding basin, which is a point that we'll return to. All right, so can I just use the mouse? Okay. No, that's it. Can I just press on the computer?
Is that where you are?
That's what I wanted. Yeah.
Yeah, so you should just be able to go backwards and forwards. Just
Yeah, let's do that.
yeah, do that. Try
Let's
that.
do that. Yeah, yeah. Okay. Okay. So on this diagram, I've indicated a lot of things. I've indicated in green the evidence, the places where we have evidence for grounded ice. I've indicated in the 2 colors of blue where we have indications of transgressions. I've indicated in red where we have evidence of emergence, and I've indicated in the blue bars the bits which are kind of solidly marine in our interpretations. This is my interpretation of the data collected by all of us. But the point of this diagram is that you see that you've got definitely grounded ice, you've got definitely emergence. As you go up in the succession, you see more of the marine material, whether it be diamictite or thicker sandstones, or in some cases siltstones. So you've got an overall succession which is showing that you've got glacial advance and glacial retreat. You've got evidence of emergence being open to the air, and you've got evidence of marine transgression and marine deposits. And overall, as you go upwards, you get more marine deposits. The overall impression from the entire section is that this sequence is staying around about base level for a very long time. So you're seeing fluctuations in water depth, which are not necessarily that extreme. No, I'm just going to do this. Yeah. So the first question I'd like to address in the context of Snowball Earth. So the Snowball Earth theory predicts, or in its original form, predicted that there was a sudden massive glaciation at least twice in the Cryogenian period, once in the Sturtian, once in the Marinoan. The Sturtian, the one we're dealing with here, starting about 715, 716 million years and lasting for about 60 million years in the model. And this was a sudden glaciation caused by a runaway albedo effect, which caused global sea ice to form all over the Earth, and glaciation down to low latitudes on land as well. That was terminated by a buildup of CO2 in the atmosphere due to volcanic outgassing, which led eventually to sufficient warmth in the atmosphere that the ice melted very rapidly. And during the period of the hard snowball, there was no active hydrological cycle. That model has changed over the years into one in which there is definitely an active hydrological cycle, as shown by the sedimentological evidence. So in some sense, I'm tilting at windmills with this part of the talk, but what I'd like to convince you is that there is an active hydrological cycle. The world in the time of the Port Askaig deposition was not totally frozen. This is an example with wave ripples. So here we have some ancient wave ripples revealing themselves on the side of a rock pool on a bedding plane. Just simply the observation that you've got wave ripples tells you that wind is ruffling the surface of the water and you're getting orbital motions in the water. Therefore, that water did not have ice on top of it. Sorry. Here you see some of the facies involved. So we've got a variety of ripple forms here. I won't go through all of them, but we've got climbing ripples, we've got wave ripples, we've got ripples on bedding forms. We've clearly got bottom currents acting throughout this sequence. Here we see some more classical sequences. These I interpret as minor mouth bars. You've got coarsening upward sequence going from dolomitic, that's the orange color, dolomitic siltstones, passing up into plain laminated sandstones, passing up into cross-bedded sandstones, on a scale of sort of 2 to 5 meters, which indicate that you've got shallow lakes into which small mouth bars are being fed by streams, not large rivers, but small streams. And these lakes have got wind ripples in the bottom of them and have got the full suite of current lane structures that you would expect in such a setting. So this is not underneath ice. These sequences sometimes contain drop stones in their lower part, but many of them do not contain any loam stones or drop stones. These are interglacial sections. Here's a nice example, beginning with the yellow surface, which is on the log on the left, and on the photograph on the right. You've got a coarsening upward sequence again, and it passes up into a thin lenticular conglomerate. This is a very non-exceptional minor mouth bar sequence incised by its fluvial channel, in this case carrying conglomerates. And there are several of these which are stacked. So there's an active hydrological cycle. There are rivers, there are deltas, there are lakes. If we go up into the marine world, at the base of member 3, we've got these large-scale cross-bedded units measured here by Roger Anderton. So the top of member 2 is an incised feature with a relief of several tens of meters, and infilling that relief, which we can prove by correlation across the island, and infilling that relief, we've got large-scale sets of cross-bedding with a variety of paleocurrents, which have been interpreted by most sedimentologists as in some way tidal. And the bottom, you can see the correlation, which shows the incision below this this tidal channel. So this is a major feature with active tides and in places with wave ripples as well. Here you see some of those large-scale cross-bedded features. These are marine currents which are flowing around as if no glaciation was nearby, but they're interbedded with diamictites. Sorry, I'll get this fixed. And here you see some of the ripple forms, climbing ripple forms, and in-phase wave ripples, which you can see spectacularly throughout member 3 at various levels. Okay, so we have an active hydrological cycle. How do we recognize that with a snowball where the entire planet is frozen and the entire sea is covered with ice? So in 2011, Paul Hoffman was, I guess, confronting that question, and as the author of the Snowball Earth model. And his answer at that time was, well, it's simple. All of the active hydrological cycle is related to the melt. So basically, the way out of this dilemma was you have a major unconformity, the Earth freezes, there's nothing happening except ice, volcanic degassing, and all of the deposits are deposited at the end phase when the thing melts. So you have a series of surging or glacial advances and retreats during the phase when the snowball is closing down. Now, subsequently, he's modified that view and now talks about a hydrological cycle which could be driven by sublimation. So in other words, you've got a frozen planet, but the water vapor is what do you call it? Sublimating from the top of the ice going into the atmosphere, and that is driving precipitation, and that precipitation is driving flux in the ice. Maybe some of the areas in between the ice are arid and like the dry valleys in Antarctica. So you can get ice moving backwards and forwards, driven by a hydrological cycle, driven by sublimation, even though the Earth is entirely frozen. And some of the climate models which have been run suggest that in the intermediate stage of the CO2 buildup, between relatively low levels of CO2, that means 100 times present for the Precambrian, but relatively low levels of CO2, you have less of a cycle, and as the CO2 builds up during the snowball phase, then the gradual amelioration of the change in the atmosphere dynamics due to the higher CO2 content of the atmosphere introduces a more active hydrological cycle. So in this world, the period in which you could have an active hydrological cycle is extended beyond just the melt phase of Snowball Earth. Which Snowball Earth, and that melt phase is predicted by the climate models which have been run for Snowball Earth to be very, very rapid. So that was always a problem. It implied that the deposition of these 47 diamictites had to happen in, to quote, a few tens of thousands of years, because that was the climate simulation suggested that you flip the Snowball Earth from one state to another very, very rapidly. So that's the modern view of how you can reconcile a totally frozen planet with an active hydrological cycle. Okay, so let's discuss that a little bit more. So if we look at the onset of the glaciation, Ian Fairchild's done some really detailed work, very careful work on the Garvelac Formation, which underlies it. And he's shown convincingly that the glaciation does not start with D1, the first diamictite of the Port Askaig Formation. It starts actually in the Garvelac Formation, which is a carbonate unit. And it starts at bed 40, where we have evidence of brecciation and emergence, and then above bed 40 and below the base of the diamictite, so between 60 and 70 meters on this diagram, you've got loam stones found within the upper part of the Garvelac Formation. So if you wanted to define the base Cryogenian, which is a case that Ian and others made in this paper, then you would define it not at the base of the Port Askaig Formation, but within the Garvelac Formation. So what does that bed look like, bed 40? It looks like this. So it looks like a frost-shattered dolomite. And bear in mind, you've now got loam stones in the dolomites above this unit. The dolomites are laminated dolomites, look like normal shallow marine dolomites, I would say, as as a non-carbonate geologist. So this would be the onset of the glaciation. Now, if this is the Snowball Earth onset and it's fairly rapid, then there should be a massive sea level drop at this time as the ice is formed and the water is taken out of the ocean and forms ice caps on the land. There is no evidence at this point of such a major drop in sea level. You've got a sequence of another 10 meters of dolomite on top, which looks very like the 10 meters of dolomite underneath. So at this place, any large eustatic low stand, which is caused by the water budget moving between the ocean and the land, has to be a bit later or a bit earlier, but it's not here. It's very difficult to make it earlier. One possibility is that you neutralize the eustatic sea level drop with subsidence. But then you're getting into the world of special pleading, because you need the rate of eustatic fall and the rate of subsidence to be more or less aligned. So if we look at this great escape, how do we get out of this conundrum that we've got a snowball Earth with rapid freezing and we've got an active hydrological cycle? Then we look for other places in the sequence where we might have a snowball unconformity. So where is the point when this snowball is hard and nothing is happening, or very little is happening? So the group looked at that, and in particular, Ian and Doug and Tony have looked at this, and Mike Hambry and Richard Waller, our periglacial experts. And there is this particular horizon above D13, the Great Breccia, in Member 1, which is called a jelly fluxion horizon. Now, what the hell is a jelly fluxion horizon? Well, jelly means jelly-like, and fluxion means flow. It's a kind of solifluxion type deposit. Looked at in the field, it's angular breccia, very angular breccia, with clasts, many of which have a vertical orientation, which forms a well-developed horizon across all the islands. And it sits right on top of the Great Breccia. And in this one particular case in Akuli, it's got this large wedge-shaped feature. So it looks as if this is a periglacial phenomena, which was a soil, effectively, for a fair period of time. And that could possibly be a break. It's clearly a candidate break for where there was a gap in this section. So maybe the Earth was a little bit behind the Port Askaig area, and the major eustatic sea level fall and freeze happened at this time on a land surface, and the bed above it is the disruptive beds is then marine. It looks like a marine series of debris flows. Maybe that unconformity surface could represent a lot of missing time. That's a possibility. I have a problem with that, and that problem is this. So if we think about the fact that we're in a basin and that this formation is 1,200 meters thick, and the one on top, the Jura quartzite, is 5 kilometers thick, this basin is going down like a train, at least a bit later than the Port Askaig Formation, and maybe during the Port Askaig Formation time. So if we've got substance going on, we can say, okay, what happens when we freeze? So sea level drops. I've in the solid blue line shown a relatively modest drop. There's a scale on the left-hand side of 1 kilometer, 2 kilometers. I've shown a relatively modest drop of a couple of 100 meters. And then that drop has to be recovered at the end of Snowball Earth, when all the water that was in ice, is locked up in ice, goes back into the ocean. And I've suggested that both of those have a finite duration. Now, the model is a bit harder. It suggests a very rapid freeze. I was reading on the train coming up how rapid that was, and few thousand years, 10,000 years, those timescales are mentioned by the climate models. And the drop is several hundred meters, because it's a lot of ice if you're going to freeze the entire planet. And so you end up with something that's more like the dashed line. Okay, so if we have substance going on at some scale, I've suggested here that the Sturtian duration is correct. Starts about 717, finishes about 660. So we've got whatever that is. I think it's 57, 50, it doesn't matter, 60 or sorry, 57 million years. Then if we've got substance going on during that time of around 1.2 kilometers, then we have to superimpose these two curves to get the relative sea level curve. So what of the eustatic fall is going to be neutralized, and what of the subsequent melt is going to be reinforced by the substance impact on relative sea level. So if we do that, then we end up with something like the black line. So we just convolve the blue line and the red line, put them together. We end up with a relative sea level curve. Now we have active sediment supply during the Garvalac Formation when we're precipitating dolomite on the shelf, maybe in the early phases of the freeze before it's become a hard snowball. Then we have no sediment supply during the hard snowball. And then we have an active sediment supply towards the end when things start melting. This is if we modify this model to include the sublimation idea, then we can move the active sediment supply more into the gap in the middle. But this is for illustrative purposes. So what happens if I've got Garvalac limestones, a little bit of glacial material at the top, freeze at the into the hard snowball, no sediment supply, and then I switch the whole system back on again as the ice starts melting or the CO2 starts building up in the atmosphere? Well, if you think about what happens with water depth, I'm accumulating accommodation space during the period when the hard snowball is there because I'm in a basin. So I'm accumulating whatever substance gives me in terms of water depth, but no sediments coming in to fill the hole. So the water depth you would expect in that model stays, it has to increase through that period of time. And then that hole then gets filled in. The hole that I've created by the substance when there was no deposition then gets filled in when sedimentation is renewed. So sedimentation should start in a deeper water setting than it finished because substance has to be carrying on during that period. Okay. And what we see in the Port Askaig Formation is, as I said, everything is roughly around base level. So we're seeing shallow water dolomites in between the diamictites. We're seeing emergence where you don't know how high that's emergent, but what we see coming in is then marine sandstones. So grosso modo, things are hovering around base level, which indicates that sediment supply and accommodation space creation are, broadly speaking, in balance. So I think that if you find a snowball unconformity in a sequence like this, in a subsiding basin, and not all Sturtian successions are in subsiding basins, some of them make space by glacial erosion, for example, then there should be a deficit which is expressed in deeper water at the renewal phase after the unconformity. Okay, so that's one issue, and I haven't done the research in the literature to go into the thick Sturtian successions and see how people have tackled this problem of accommodation space continuing to be created during the hiatus. I think it would be a good test of the model. The third thing I'd like to quickly mention, so we looked at active hydrological cycle, we looked at the substance deficit or the great escape, and I'd like to look at non-actualistic features. So what can we not understand from present day features, present day processes about what we see in the Port Askaig Formation? This is a beautiful example of the top of D22, which has got these wedges, these frost polygons. Everyone agrees they're frost polygons. It's a top surface of a diamictite infilled with cracks, which are infilled with a fairly mature, angular, reasonably well sorted sand. Okay, and then the little skim at the top of the diamictite has been washed off by the waves, so the dikes are standing proud. Now, everyone agrees they're frost polygons, but everyone agrees also they don't look like anything like modern frost polygons because they're about 10 times too small. So the scale of this whole thing is 50 centimeters. These things should be on meters scale. So polygonal features, which you see in periglacial areas, are a lot larger than this in general. So that's got people struggling a little bit. These are not uncommon. This is a compilation by the team of areas where we find these wedges on top surfaces, and they're on very many different horizons. So 25 horizons have been identified with periglacial features. That includes the wedges, that includes frost-shattered stones, for example. And those are shown on this diagram. They're scattered through the entire unit. So what might this indicate? Well, it's clear that these are periglacial. If you, there's a beautiful piece of work by Mike and Richard, where they looked at a comparison of the roundness index of stones within the diamictite and stones which are lying on top of the diamictite on the surfaces on the tops of these diamictites. And you can see that in blue, you've got the roundness in the diamictites, and in red, you've got the angularity, which is much, much greater of the material on the top. So you're seeing frost shattering, you're seeing the angularity which you get through mechanical weathering in a periglacial environment. One possibility for the relatively small scale of the frost polygons is that you're dealing here with an equatorial glaciation rather than a polar glaciation. So in a polar glaciation, the freeze-thaw cycle is essentially seasonal, summer, winter, whereas in an equatorial situation, it could be diurnal. So the actual change night-day may be something. So you may be having a much greater intensity, a much tighter frequency of freeze and thaw in the equatorial situation. And that diurnal seasonality, no, okay, leave that there. What we also see is this clast fracturing on the very tops of the surfaces, in addition to just the angularity measurements. You also see individual fractured clasts, and it's really fantastic. You can go there and find all 4 bits of one clast. They've just been moved 1 centimeter away from each other. You can just put them back together. You can just fit them back together on the top of these diamictites. And that is fascinating, not just because of the frost shattering, but because of the preservation that those things have undergone. So whatever, these are on the top surface of the diamictites. In some cases, what immediately overlies that is subaqueous deposits, but those stones haven't been moved at all. They're just lying there on the top of the diamictites as they were frost shattered. We'll come back to that. This is an example in point of the top of one of these diamictites. This is D24 on the Holy Island. And here you can see the stones within the diamictite. You can see a collection of more stones, perhaps a deflation lag at the top of the diamictite. And then you can see what's probably windblown sand at the very top of the sequence. And that windblown sand is then going down into these cracks. So you're getting superb preservation at the very top of the diamictite to see these periglacial features. And I think that's due to aridity. I think what's happening in this situation is that you've essentially got an arid system where very little rain or snow is falling on these diamictites and causing stream erosion of the top. You see that in a few cases, but it's exceptional. In most cases, you just have this of subaerial emergence. You have very delicate preservation at the top. And this is an extreme example. This is a correlation panel across the islands, and the one in the middle, which has got the odd section with the big cut taken out of it, this is Lletha Cwyn. It's a small skerry in between the main islands, and it's got a section which is just anomalous. It's anomalous in many ways, but in this particular way, you can see that it's been correlated here on a datum, which is a wave rippled horizon on top of the D26. Is actually there's an involution horizon, a periglacial frost heave horizon. Then there's a post-glacial transgression, and you've got wave ripples all across it, and you start getting this deltaic sequence on top. It's a beautiful datum. You hang on that datum, and then you suddenly realize that at the top of the section you've got a datum as well, and in the middle all hell breaks loose. And in the middle where all hell breaks loose, you've got that red line showing a paleo valley, which has been incised into a stack of 3 diamictites, D27, D28, and D29. And the interesting thing is that the top of D29 has frost wedges indicated by the little orange V's on the shoulders of the paleo valley. The paleo valley has got in the bottom of it maybe less than 2 meters of fluvial sandstone, fluvial cross-bedded sandstone. And then it goes into a deltaic section with a bunch of climbing ripples. So you've got an incised valley with a relatively small stream channel at the bottom of it. There's then a flooding which infills that valley with water, it's standing water in which I can produce climbing ripples. But on the shoulders of that valley, nothing is being eroded. I essentially have the preservation of frost polygons on the top of the diamictites, which are on the side of that valley. And I think one solution is that we're dealing with groundwater transgressions. So what's actually happening is, rather than erosional transgressions where water, marine water or lake water is flooding back and reworking the tops of the diamictites, essentially the system is so arid that the groundwater is just seeping up and it's rising. And then eventually you find yourself underwater, but there is no energetic transgression. And that accounts for me for the beautiful preservation of these top diamictites. And aridity is actually something which is predicted by the global Snowball Earth model. They predict an arid equatorial setting during this phase of global freeze. So that's something which is in accord with the model. I mean, many Snowball Earth papers you'll find is consistent with is the phrase that's used. So that is certainly consistent with. And aridity can help us explain some other things. There are gypsum pseudomorphs in the Garvalac Formation immediately before the basal Port Askaig Formation, but within the glacial period, so above bed 40. And there are anhydrite nodules in the Losset Formation as well, so which is older. But there is at least evidence that there was aridity during, there was gypsum precipitation at least during the glacial period. Okay, so if we come back to our Great Breccia and our jelly fluxion horizon, on top of it, immediately overlying that, we have a single bed of large-scale cross-bedding that's shown here. And we have that's dolomitic, that unit. And this dolomite unit sits right on top of that jelly fluxion horizon. And one possibility, Ian Fairchild is the guy you have to come and have talk to you about the dolomites, but I'll do my best. Dolomite is a weird mineral in that it should thermodynamically at least precipitate out from seawater, but it kind of refuses to do so kinetically. And that's probably due to various features like trace element chemistry and maybe even crystal ripening, austral ripening, or different ways in which you can promote or inhibit dolomite precipitation. Here we've got dolomite in this cross-bedded unit, which has got climbing ripple cross-lamination at the bottom of it. It's got a siliciclastic material. And this one possibility which Ian is working on for this is that this could be a springline dolomite. So associated with that jelly fluxion horizon, if you had a groundwater table rising, you've got a frozen climate, which is essentially very evaporitic, then maybe you get dolomite precipitation associated with groundwaters coming out essentially on a spring line. It's a weird deposit, is what I would say. The other dolomite, the upper dolomite unit, is a bit easier to understand in that the base of it is actually a discordant surface, and it's immediately overlain by features which look stromatolitic. I've indicated them in the lower right of this slide, and the little yellow line shows some hummocky lamination. So there appear to be some algal laminites at the base, which is okay for a dolomite. The rest of the dolomite doesn't give its secrets away very easily, I would say, but Ian managed to find this revealing outcrop on Holy Island on the bottom left, which shows these dolomite fragments in a matrix of siliciclastic material. This appears to be a dolomite conglomerate. There's also concretionary formation of dolomite going on in this unit. But this is perhaps a storm-generated or a wave reworked conglomeratic dolomite. So these things are enigmatic, I would say. One thing about the dolomitization that's, I think, worth bearing in mind is that we've got these fluctuations of glaciation, we've got marine conditions, we've got arid conditions, We've probably got groundwater tables moving up and down in line with the ice advance and the ice retreat, and maybe with the aridity or the precipitation of more snow and rain. That is going to mean that this section had a complicated history in terms of its formation water development. So at times there could be marine flooding. You can then have essentially salinization of the aquifers. And then at times you've got the ice advance and you've got fresh water percolating into the aquifers. And therefore, I think that for me accounts for some of the features where you see dolomite formation in what look like low energy lacustrine deposits. So it could be marine formation water penetrating into actually a terrestrial deposit due to these fluctuations in water tables. So not necessarily is all dolomite marine. The next thing to say is that there's iron. In many of the Sturtian glaciations, there are iron formations. The outcrop on the right is the one that has had the most effect on my clinometer of anything I've ever seen as a geologist. It moved at about 40 degrees. So these are magnetite-rich layers. That particular one is at the boundary between member 1 and member 2. And on the left, the blue-colored siltstones and mudstones in the disrupted beds, which Doug Ben is standing next to. These are also iron-rich. This is common in Sturtian glaciations. It's almost distinctive, I think, in Sturtian glaciations, but it's also a feature of the Neoproterozoic ocean in general, that there appears to have been if you like, a resurgence of iron formations. What you need for an iron formation is you need reduced iron to come into the water, because only the reduced iron is soluble. You then need to oxidize it in some way to make it come out of the water. And the thought is that the oxidation could be related to meltwater. So the Snowball Earth argument is that fresh oxygenated meltwater, which is coming in from glacial melt, is actually the oxidant, and the lack of sulfur input into the ocean during the glacial period, because of runoff being generally reduced, means that you don't have the sulfur to precipitate the iron as pyrite. So you essentially precipitate it as hematite, and this is now magnetite, but that's because it's green schist facies, so it's gone through a metamorphic phase. Okay, so is the Port Askaig Formation Sturtian? Well, unfortunately, in Dalradian we have very few dates. I think Tony Prof probably said a few words about that. But we have got, thanks to his work, amongst others, composite isotope curves, and that's really what we have to rely on. This is the carbon isotope curve showing the Sturtian, the Marinoan, and the Gasquias glaciation with the excursions in between. And there are also a series of anomalies where the carbon cycle went on tilt in between these, in particular the so-called Islet anomaly and the Trezona anomaly and so on. But the key isotope record for the Sturtian is perhaps the strontium. So here we see a global strontium composite on the right-hand side. What we see is the data for the Port Askaig Formation in the column, which has got SR written on it. And you can see these relatively low strontium 87-86 ratios just prior to the Port Askaig Formation, which is absolutely in line with what the Sturtian would predict. So that is not spectacular, but it's certainly quantitative data which says that it's in line with the global strontium sea level curve, and therefore this is likely to be the Sturtian glaciation. And I think for me it makes sense in the broad Dalradian picture, which is what we're going to look at next. Okay, so what does this formation tell us about the Dalradian? So the first thing is the onset of the Sturtian glaciation. Now, the Snowball Earth model, as I said, predicts that the onset is rapid and the cessation is rapid. The data for the cessation, in my opinion, is not as good as the data for the onset. If we look at the data for the onset here, this compilation from Francis MacDonald, you can see in black the age dates that are available. The ones with arrows pointing up means younger than, the ones with arrows pointing down means older than. And then we've got some dates which are around the the edge of the glaciation. And you can see that, you know, this is old rock, and we're converging within 1 or 2 million years, which I think is pretty good going. And these are uranium lead dates. There's not rhenium osmium data on this plot. And those data align a little bit, well, pretty close to the Franklinian large igneous province in Arctic Canada, which is a major, it's probably the largest igneous province of the lot that we know of so far. And those dates, those are Baddeleyite dates, and the red and the blue are from 2 different sorts of volcanics. But those are lining up around the onset of the Sturtian glaciation. So people are now looking for a relationship between the CO2 output and the flip of the planet into an ice age, which I don't profess to understand, but there we are. Okay, so if we take the base, if we say it is Sturtian, and the Sturtian started globally around the same time with the data that we have at the moment from, it has to be said, I didn't mention it, but those black data are from several continents, right? So it's about 4 continents worth of data represented there. So if we take that as 717 as a date, then we can say, okay, what does this tell us about Dalradian substance? Now, this is the Manuel model of the Dalradian substance. So it's I know nothing. Okay, and what you've got here is the dates at the base, the monzonite dates, and then you've got the one date that we hang on to, which is the felsic rock with the pillow lavas at around 601 million years. So if you just say, well, it's about 20 kilometers thick and it took that long to deposit, I know it's not 20 kilometers thick in any one place, but if you just take the Manuel model, then this is what you end up with. And if you drew a straight line through the data, the Port Askaig Formation would take about 10 million years to be deposited. Okay, that's not right, but that's what happens if you follow Manuel. Now you can do a bit better than that, because Tony and Dan Condon did some work, and they established this trinity. So we've got the Port Askaig, we've got the Stralinki conglomerate, and then we've got the Lochnakiel boulder bed on top. So if you say that those are the Sturtian, the Marinoan, and the Gasquias, then you can put those on the plot. And if you take their times and you plot the same data through it, then you end up with this. And you end up with a sort of nasty kink in the Port Askaig Formation. It's deposited much slower than everything else. Okay, so that's interesting. It gives you 60 million years from for the section from the Bonahaven to the Tevallic volcanics, which is a kind of passive margin sequence, rift to passive margin sequence. That's a bit quick, but it's not impossible. And it gives you and it honors the Sturtian duration. So that's another possibility you can do using those as dates. What you could also do is you could say, well, why was the Port Askaig Formation taking apparently so long to be deposited relative to the rest of the sequence? And you could then say, well, okay, maybe it's 2 different basins. So maybe the Argyll group, Appin group boundary is actually significant in basin terms, and we're dealing with a slower rate of substance up to and including the Port Askaig Formation, and a higher rate of substance when the rift kicks in, go through to the passive margin in the younger section. Now that is an interesting idea. We can toss that one around and discuss it. Tony Prave proposed this model a long time ago, I think when he first came to Scotland about 20 odd years ago. And he suggested that the Grampian group and the Appin group were fallen basin. Well, that burial curve is not a fallen basin. It would be the other way up, because it would be slow at the beginning and fast later on. But nonetheless, the idea that you've got a change in substance rate around this time would reconcile the data that we have with the global duration of the Sturtian. Having said that, I don't feel compelled to reconcile the data with the global duration of the Sturtian. I think that's an open question. Okay, and then if we look at this worldwide, we are looking, as I said, at a basinal deposit here. And I think it would be interesting to look at the other basinal deposits. So some of these units are extremely thin, the Sturtian glaciation. And there's only a few of them on that list, which you can say, okay, that's clearly in a good basin that's subsiding rapidly. And I think this point of interrogating how the unconformities of sea level rise, sea level fall express themselves in a substance setting is a good test. And I'm looking forward to reading that literature for chapter 16 when I get the time. Okay, coming back to this point of did the Dalradian change at this time, then I've worked on the Jura quartzite. I talked about it here a couple of years ago. And it's clear that at that time, you've got separate subbasins developing. We don't know, we know that the Port Askaig Formation is developed in Ireland, maybe and in Schiehallion area. But it's not clear to me that there's evidence. We don't have sufficient outcrop to know what the extent of that basin was at that time. Let's put it that way. We've got selected outcrops. But if other people have more information on that, I'd be glad to hear. So that's just some pretty pictures. I'm running short of time, so I'll skip on. In terms of what is the syntectonic story of the Port Askaig, this is a correlation diagram which goes from our Garvalak Islands, where we spent most of the talk, onto Isla. And you can see that the base of the unit is missing on Isla. There's an onlap relation. So we've got basically member 2 coming down and onlapping. So there's evidence, if you will, of a footwall block, certainly a basin margin, which is being onlapped as you come from the Garvalaks onto Isla. So this isn't a layer cake stratigraphy. Interestingly, the unconformity of the onlap on the top of the Great Breccia is around the time of that jelly fluxion horizon. And I think that the oddness of the Scaer-Lether-Cohen sequence, which expresses itself not just with that one incise valley, but with a series of different stratigraphic relations around a point of the red arrow, you can see on these datum cross sections, it's a serial offender in terms of not conforming with the stratigraphy of the rest of the island. I think that's probably controlled by Sindhi positional faulting. But these faults are on the order of 10 meters, 20 meters. This is nothing of basin significance. I was excited to find it, but it's probably irrelevant in the big picture. Now, in terms of low latitude glaciation, just a quick word. The evidence for low latitude glaciation is not dolphins springing up into the air. The evidence comes from paleomagnetics. I just want to, I followed this trail because I thought, how do we know? People quote 35 degrees south as the paleolatitude for the Port Askaig Formation, but we've never got any measurements from it because they've all been reset in the deformation. So I asked myself the question, what is the audit trail? And I kind of wished I hadn't at a certain moment, but on the right, you've got Rodinia as compiled in 2013. And then on the left, you've got Rodinia 4 years earlier, compiled by similar authors. And I draw your attention to Baltica. You can put Baltica where you want, I think. You can also choose its rotation. Actually, the degrees of freedom for Port Askaig are not that great. If you concede that it's part of Laurentia, then there are good poles for Laurentia at this time from those same Franklinian LIPs. And those are good magnetic data, and they're from sequences which haven't compacted. One of the problems with low latitude glaciation is that if you compact sedimentary rocks, then you end up with lower inclination angles. And so you need to be wary of that. But if you're doing dikes, then it should be okay. But okay, so if you assume that the regional North Atlantic geology puts the Port Askaig Formation next to Laurentia, then you can use the Franklinian poles, and then you end up at about 35 degrees south. That's where the audit trail goes. I was very intrigued by, I don't know who reviewed this paleomagnetic paper on the right-hand side, but you see that I've had to put the latitude lines on myself. It's kind of ironic that paleomagnetic reconstruction included all the figures that were global maps. None of them had latitude lines labeled. I could only work out what they were because there was one of the present day where they'd taken the sites, and I knew the latitude of New York. Okay, so if we move on to provenance, let's quickly looking at paleocurrents. So where did these sediments come from? The paleocurrents are frankly all over the shop. This is my mental model for the depositional environment of member 2. This is the Mackenzie Delta. So this is in between glaciations. And I've indicated there on red paleocurrent measurements off the satellite image. And on the left-hand side, you've got on the outer ring strikes, and on the inner ring, you've got flow directions. And you can see that they're all over the place. In other words, there is no major paleo slope. So we aren't saying anything about provenance from paleocurrents. We're just talking about transport directions, very local transport directions. And this is the diagram which Tony really wanted me to show. This got an audible gasp when it was exhibited at the Geological Society when Tony was doing his PhD. That is the sum total for the formation. So good luck with the paleo slope. In terms of the ice advance direction, we have 15 horizons where the team has identified glacial advance. And those are illustrated on this diagram. They were on the one at the beginning with all the complicated lines. And the sum total is towards the northwest. So I think we're reasonably confident that many of these sequences where we can get indications are consistently towards the northwest, including the famous bubble, the fold on Holy Island, which you see there. That's an orthorectified drone image. So we got a fantastic help from drone imagery taken by Doug and Jordan on this project. Okay, so glaciotectonic. Oh, I don't know what's happened there. And then we've got the classed counts, which in essence shows an inverted stratigraphy. You get more granitic material as you go upwards, and you lose the dolomitic material, which can be associated with the underlying subjacent formations. So, and we haven't got a firm, we haven't got data which tells us, which ties the granitic material to a source area. Okay, so and then the last point on provenance is that in member 2 times we start getting a more mature petrography coming in, relatively well sorted sandstones. It's moderately to well sorted sandstones. This, for me, is the incoming of the Jura quartzite petrography. So during the Port Askaig Formation, the drainage basins are reorganizing such that we get this extra basinal mature subarcosta quartzitic material coming into the basin. And that happens in member 3 clearly, but it probably starts already in member 2. So there is a reorganization, at least in terms of drainage basins, which is happening as you go through the Port Askaig Formation. And that may be relevant as you move towards the rift basin of the younger section. Then to finish, I'd like to say a few words about sequence stratigraphy, but this is going to be very short. So this is a drone image, which on the southwest end of a coulee with a log section put on it. We're able to map beautiful fluvial incisions on these images and in the field. That's about a 5-meter down cut on the right of the log. And these are fluvial channels which are incised into the section underneath. You've seen the Paleo Valley in Sgurletha Cuin with the shoulders of the emergent diamictites on both sides. So this is relatively deep incision. So we can begin to talk about sequence boundaries and flooding surfaces. And but there is a complication in terms of interpreting those sequence boundaries and flooding surface. What I've got on the left here is a model. So all models are wrong, but some are useful. There's a model on the left-hand side, which is showing the present day rates of relative sea level change, which is attributed to isostasy. So what you're seeing is uplift in the polar regions. You're seeing deflation in the equatorial regions. This is the mantle flow, which is occurring today as a result of the delayed recovery of the polar ice caps. So material is moving from the equators poleward. And that, in terms of ice advance and retreat, which we can clearly see with our 47 numbered diamictites, and God knows how many there actually were. I mean, I remember being taught there were 4 glaciations in Europe, and then Nick Shackleton came along with oxygen isotopes and said, no, sorry, there were about 28. But so we haven't preserved every glaciation. So the ice is going backwards and forwards. What you'll get is a substance under the load, and then you'll get a forebulge effect. And those will be occurring on a timescale of isostatic recovery, which is delayed with some lag time from the glacial advance and retreat. Now, with that kind of relative sea level background, I think it's going to be impossible, frankly, to work out what the significance of these unconformities is with respect to glacial advance or glacial retreat. So sequence stratigraphy we can use as a methodology to describe what we see, but I don't think we're going to be able to interpret it in terms of base level advance. There are sequence stratigraphic models. This is Zekin et al. And one of the et al. Is Coutinho, the Basque guy, whose name I can never pronounce, but he's the guru on sequence stratigraphy. So this has been attempted. What I would say is that there is a sequence which I'd like to know more about that's been described in McMurdo Sound, where they've got cores, they've got continuously cored sections for about 1.5 kilometers through these grabens, which is a Eocene and younger section where you've got glacial deposits related to an ice sheet, which are in an active tectonic setting. And this is an area which I need to know more about in terms of a potential analog for the Port Askaig Formation. And there they describe a series of motifs. And the motifs that they describe is shown in this diagram. And it's one simply of advance and retreat of ice. So they pick a sequence boundary underneath the ice advance, and then you have a flooding surface in between the glacial advances. And then you have outbuilding proglacial deltas of various sorts, some ice contact, some not, as the ice advances again. And that motif, if we talk in those terms, you can clearly see in the Port Askaig Formation. And I think an example is shown there, those particular sequences. D25 is a particularly beautiful one. It's a coarsening upward sequence, which is full of granule dropstones. So it's a kind of distal glacial marine section with a clear maximum flooding surface. And then, so I can put sequence stratigraphy on my diagram. Gray is diamictite, blue is flooding surfaces, and red is sequence boundaries. But the significance of these in broader snowball terms, I wouldn't dare to conjecture, to be honest. So in conclusion, active hydrological cycle, yes. There's no doubt that deposition of this sequence occurred during an active hydrological cycle. Hard snowball, no. I don't understand the substance issue. If we've got a completely frozen section and we've got no active hydrological, well, if we assign the active hydrological cycle only to part of the sequence, I end up with this problem of creating a hole in the ground because the mantle does not know to stop subsiding whilst the Dalradian basin is forming just because it's cold outside. Okay, the non-actualistic deposits, I'm scratching my head about the dolomites. Ian's made progress on that and is in the positive direction in terms of some of these ideas like springline dolomites. And then we've got this question of the aridity, which I think is a kind of light that went on last year amongst many of us, and we all said, yeah, I can see that working. And I think for me in particular, the evidence is the lack of transgressive erosion and the preservation of these delicate features. So that is something to think about in terms of what you do in a section which is basically not got a lot of water flowing around for a lot of the time, even though water is flowing around. Is it Sturtian? I think the answer is most likely yes. I think I showed you the strontium data. We've got the ironstones. We don't have a capped dolomite, but many Sturtian glacial sequences also do not have a capped dolomite. Paleo latitude 35 degrees south looks plausible. It's a chain of reasoning. You've got a pole in northern Canada. There's also a pole in Wyoming. So you need at least 2 per continent to know how to rotate them. But that looks reasonable. Dalradian, it's interesting to think about Tony Prave's old ideas about basin reorganization and how the Port Askaig might fit into that. I haven't grounded that out. Provenance, there is evidence for a basin reorganization in terms of this extra basinal quartz-rich source, which is beginning to come in Port Askaig time. And sequence stratigraphy, it's complicated. The last point I think I'd I'd perhaps mention is that one of the, if you think of the whole sequence as being, well, one of the things you have to explain is that the sequence tends to become more marine upwards. So it starts off marine in the Garvalac Formation. There's definitely some significant terrestrial deposits in member 1, member 2. Member 3 has got intercalated marine sandstones. Member 4 looks as if the diamictites could be marine. Member 5 has got marine section in it. So it's getting more marine upwards. So maybe the substance rate is increasing upwards through the formation. And maybe that's a point that we have to bring in to the thinking. So thank you for your attention. I'll do my best to steer clear of any debate, but I'd be happy to take questions.